All right, so it looks like we've got some attendees on board. So thank you all for being here. Thanks for joining us. So we're super excited to have this virtual summer camp. So we had our first week last week and it went really, really well. I really enjoyed teaching it. I enjoyed making all of this curriculum and it's all of it is just cool. Literally all of it is fascinating. So it's super fun to teach about, and it's since we have so many guest speakers that are going to be joining us throughout the week, y'all are going to be learning a lot of things, and I'm also going to be learning a lot of things, which is my favorite part because I love to learn. So my name is Galen Gross, and I work for the Marine Education Center, and the Marine Education Center is an outreach branch that is off of the University of Southern Mississippi. So the University of Southern Mississippi is a college campus in Hattiesburg. And we are basically just a satellite campus that is located on the Mississippi Gulf Coast. So we're in Ocean Springs, Mississippi, and we focus on marine studies. So we're also part of the Gulf Coast Research Laboratory. So that's going to be where all of our science researchers are. So pretty much the people who work for the university that are like professors, right? So they're going to be teaching college classes, they're going to be conducting their own research, and they have lots of different classes that they teach at the Gulf Coast Research Lab, and then there's tons of labs and cool things to see. And so what we are is we are the outreach extension off of the research lab. So basically we take all of the information that the scientists gather, all of their research, and just basically their key findings, what they figure out and what they're working on, and we present it in a kid-friendly format. So we have lots of different field activities that we do on a normal basis outside of COVID-19, right? So what we're usually doing is field trip outdoor activities that students can come and do. So usually it's lots of school groups in the school years. So we have lots of like classes that come to us. Teachers will bring their students, and we will go out and do fun things like kayaking, or we'll go out to the barrier islands. We go out to Ship Island a lot. And then we'll also do things like go sharking. So when we go sharking, yes, that is a verb. When we go sharking, we will go out on a research vessel that's owned by the university, and we will get to put out a hand line, and then we will also get to rod and reel for sharks. So what happens is we catch a shark, we land it, put it onto the vessel, and then we will have the students help us to weigh it and to measure it to figure out how big it is. And then we will tag it. So we'll just put a little tag on their dorsal fin, and the students get to do that. So that's usually their favorite part. And then we release the shark, and it goes back into the Mississippi Sound or the Gulf of Mexico, whichever side of the island we're on. And yeah, so the students really, really love doing this. And this is all of this information that is gathered from the sharking goes to back to the research lab, and they use that in the shark labs. And so pretty much we are just a facility that makes science more accessible for students, and it's super fun. And yeah, so what we're doing now is we're doing virtual summer camps. So I have hosted the Blue Planet Camp, which is, let me share my screen with you so you can see our first slide. So we're going to be talking about oceanography and ocean engineering. So these are kind of two big, broad fields that are super interesting and popping right now. So I got my bachelor's degree from the University of Southern Mississippi in marine biology. And so I had to take some oceanography classes, and I minored in geography. So whenever I did that, I got to take a lot of like climatology classes, and I learned a whole lot about the atmosphere and how it interacts with the ocean. And so that sparked a really big fascination for those phenomenon for me. But in oceanography, you have four major principles. So you have physical oceanography, you have biological oceanography, chemical oceanography, and geological oceanography. So we're going to be talking about all four of these. And so the physical oceanography is what we're going to be focusing on today, which is mostly going to be talking about just like the processes of the ocean. and how the water is moving and things like that. So biological will go into a lot of the organisms. We'll talk about what's alive, right? Because that's what biology is. And then in chemical, we'll talk about the things that are not alive, that are just chilling in the ocean, that are super important. And then in geological, we'll talk about some sand and some different types of materials that are also found in the ocean that are visible, whereas our chemical ones are going to be invisible. And then we have ocean engineering, which is our bonus lesson. And we're going to be talking about just some of the different types of tools and the field equipment that is used when you are researching and studying as a marine scientist. Super, super fun equipment. It's kind of like playing with toys all day long, but big people toys and expensive toys. So without further ado, let's get started. Thanks for being here. And I hope you stay the whole time because you're just so fascinated by all this information. So we have a couple poll questions for you to begin with, just to kind of get us started, see where you're at. How much do you know about the ocean already? How many oceans do we have? Think about that for me. Like I said, I minored in geography, so I really love a good map. So how many are on the map? And we have a couple of different answers that we've been given. So some of us said 2, some of us said 4, and then most of us said 5. So 5 is the correct answer. We do have 5 oceans, and they are going to be the Pacific Ocean, the Arctic Ocean, the Atlantic Ocean, the Indian Ocean, and the Southern Ocean, which is kind of one that people will forget. So why do we have 5 different oceans? They're going to be, because really, if you think about it, it's really all one connected body of water. But they're going to be separated into 5 different oceans based on a couple of different characteristics of things like their depth, how much salt is in it, or just like their overall water quality, the temperature of the water, those kinds of things. So each ocean has its own kind of unique uniform as a body of water. And so as those things change, you kind of enter into another ocean or a different body of water that's still all connected. All right, so what type of water is in the ocean? Go ahead and answer that one for me. Do we have fresh water, do we have salt water, or do we have brackish water? What's in the ocean? You have less options on this one. There's only 3. And 100% of you said salt water. Perfect. Yes, so there is salt water in the ocean, and that is going to be lots of different things dissolved in your water that's going to create that salt in there. All right. So we are going to go ahead and get started. So what is physical oceanography? So physical oceanography is going to be the study of physical properties and dynamics of the ocean. So this can include all these different things that I have bulleted here. So it can include how the ocean interacts with the atmosphere, so with wind and rain, the air and the sun, how the ocean responds to changes in temperature, how land changes in response to ocean movement, how water masses form. So we're talking about things like waves, tsunamis, gyres, storms, right? How currents form and what currents are, and then also sound waves. So that's kind of one thing that you don't necessarily think about all the time, but the sound is going to be traveling at different speeds and at different depths of the ocean. And then it's also just going to be manipulated by the quality of the water, which is kind of an interesting concept as well. But what we're going to be talking about mainly are these 3, because I can't go through all the bullets, right? That would be like a whole college class, and we're not doing that. So we just have 1 hour with you guys. So we're going to be talking about how the ocean interacts with the atmosphere a little bit. We're going to talk about how the ocean responds to changes in temperature. And we're going to talk a little bit about currents. So these are the three major things that we're going to be talking about today. And what does that look like? So currents. There are different types of currents. Some of them are going to be created by wind, and others are going to be created from changes in water density. So what is the density of water? Not the actual number, but just what is density in itself. So density is going to be basically like how compact or how loosely or far apart the molecules are. So in fresh water, the molecules are going to be kind of spread out more. They take up more space. And so they're going to be kind of spread out. And then in salt water, it's going to be more dense. So those molecules are going to be closer together, which is going to just kind of make a more compact water. And then your water density is going to change as well with the temperature. So warmer water is going to be less dense, and then cold water is going to be more dense. So the density of the water is going to kind of create movement. So if you think about it, as water is at the surface, right, closer to the sun, it's going to warm up. And so that warmer water is just going to sit on top. But sometimes it can start to cool. And if it does cool, it's going to sink down to the bottom. So I'm from Mississippi. So obviously I have gone swimming in, a really muddy lake in my life, because that's just how you grow up down here with the alligators. And so if you've ever like jumped off of a pier or off of a dock or something into that lake, and the water is really warm, and the farther down you get, it gets colder and colder, your feet get cold. So that's going to be due to the density. It kind of creates this gradient where the warmer stuff's going to be at the top and the colder stuff's going to be at the bottom. But this can also translate into these types of water themselves. So obviously these two things don't happen on their own. Fresh water is going to be either warm or cold, and then salt water is going to be either warm or cold. So which form is going to be the most dense? What is the most dense type of water? If you took the two things, or the two different types that we have here, four different types, I guess, and you combined them, what's going to be the most dense type of water? We have warm fresh water, we have warm salt water, cold salt water, or cold fresh water. Which one do you think is going to be the most dense? Very nice. Cold salt water. 100% of you said that. Perfect. Yeah, so that colder salt water is going to be super, super dense, is going to be closer to the bottom. And so this is going to create a lot of our currents. So if you look at this image here, this is showing you the global conveyor belt, which is a massive process. As you can see, it goes over the whole globe. And it's basically just the movement of water with deep water currents and surface currents. So the deep water currents are going to be super deep down, so they're not going to be created by wind. They're going to be created by that change in density. And so the surface currents are going to be the ones at the top. They're usually going to be warmer. On average, the bottom like of the ocean floor is 4 degrees Celsius. So that is 4 degrees above freezing. So it is very dense because once it does freeze, we know that ice is going to be less dense than water, than liquid water. So at the closer it gets before freezing, it's going to be getting progressively more dense until it freezes. And all those molecules just like stop, right? And then they're going to be spread out and just stopped moving. So that's what happens when water turns to a solid. So this is the global conveyor belt, and it is going to be circulating our water all across the world. And this is a very important process. It's going to control a lot of our climates, and it's just going to control a lot of our weather overall, and also just the movement of our water and what is happening with our oceans. So this is the global conveyor belt kind of broken down a little bit to where you can see where it starts and where it ends up. So the beginning of the global conveyor belt is going to be up here in the Arctic, and this is going to create a coldness in the water, and the water is going to start to travel. So it kind of starts to go down south into the Atlantic. And then as it moves farther, it's going to cross over the Southern Ocean. And then once it does that, it kind of splits. It turns into two different currents. And so it can either go up or it can keep going this way. So as it's moving upwards, it's eventually going to get to a point where it starts to warm up. And so that could be from a number of different things. It could just be because it's getting more shallow, right? So it's moving into a more shallow ocean, right? So the Indian Ocean. And it's going to start to warm up. Same up here. So as it kind of loops around up here, it's kind of starting getting closer to the equator. So it's kind of getting warmer. And then you have all of this, right? So what is happening here, whenever we have our water that is moving in this fashion, so it would take about 1,000 years for one parcel of water to make it back to the beginning of the global conveyor belt. And that was tested. It was an experiment, but they didn't track one parcel of water the entire time. So what happened was they took the speeds of the currents. They were able to take just the rate of the water moving and the distance of how far it was going and all of this information to calculate it. So they had to do a little bit of math. Right. Science does involve some math, which isn't everyone's favorite, but it usually leads you to the cool thing that you're trying to figure out. So it would take 1,000 years for one parcel of water to travel all the way down and back up and then come back to the Arctic. So this is the global conveyor belt, and it's just one way of the ocean water moving. And this is mostly going to be due to density. So another way our water moves is going to be currents. So these are wind-driven surface currents. And as you can tell, there's a whole lot happening here. You still have those changes in temperature. So you still have some currents that are going to be warmer and others that are going to be colder. But a lot of these currents are going to be moving in directions that are going to be affected climatically. So like the climates are going to be changed based on the temperature of the water, which is really, really cool. And so like you have your equator right here, and all these currents are going to be changing with the wind patterns and also with the way that the earth is tilted and the sun is heating up the equator, right, at that direct point. And so your currents are going to be moving with the wind and with the heat from the sun. So why do the surface currents move in so many different directions? Well, because the wind is moving in so many different directions as well. So if you look at this, this is kind of a complicated image, but it's just showing you a little bit about what our winds really look like and what's happening. So you get these cells on either side, they're basically all over the globe, right? They're like 3D coming off of the globe. And they're going to be circulations of the wind based on that kind of the same concept of like heating up, the air heating up or the air cooling down. And so it's going to create this circular movement. So as the air heats up right here by the equator, it's going to rise. And then once it gets to higher altitudes, it's going to cool and sink. And so that's just going to be happening. And by the poles, it's going to be already naturally cold because of the tilt of the earth and where the sun is positioned. So that air is just going to sink. And then as it gets warmer, it's going to rise back up. So these processes are going to create other winds as well, but they're also just going to be creating these cells. And so each cell is going to be called something different, right? The Hadley cells are going to be the ones that are in the tropical regions. Then you have your mid-latitude cell because mid-latitudes, right? And then you have your polar cells because it's by the poles. But in addition to that, you also have all these other winds that are happening. And so the winds are going to be named based off of where they came from. not the direction they are going. So like these are called the Northeasterly Trades because they're coming from the northeast. These are called the Southeasterly Trades because they're coming from the southeast. Currents are going to be named oppositely. They're going to be named based on where they are going. So that makes things kind of complicated. But your winds here are going to be affecting your currents very much here. And so this is us, right? We're here. So all of these currents you can see are kind of moving in our general vicinity. So what happens with the wind and currents, you get something that's called the Ecumene Spiral. And so the Ecumene Spiral is going to be a process of the wind moving the water, creating that current, but it can only happen up to 100 meters in depth. So if this is your water, right, this big arrow is your water, the wind is going to be blowing and it's only going to be strong enough to move water up to 100 meters. So the Ecumene Spiral is going to be how the water is moving based off of the wind. So it can only be affected for 100 meters down, just because, like anything, the wind isn't going to be affecting the ocean at super deep depths, right? It's not that powerful. So as the wind pushes water, it's going to get weaker and weaker, the impact. And so it's going to be basically moving less and less water as you get deeper down. And so the initial strength of the wind pushes the water at a 45-degree angle. And so you get this motion of the water moving at 45 degrees from the wind. But as that wind is going to be pushing the water deeper down, that 45-degree angle is basically just going to get larger and larger away from the wind. So it's going to kind of be like a clock like that, right? And so that is going to be changing the net transport of the water. So just basically overall, the water that is moving from the wind is going to be moving at a perpendicular position from the wind. And this is going to be happening like if you were out on the boat or something like that, and you were thinking about the wind, or it was really windy that day, you should be able to look at the water and kind of tell that it is moving perpendicular. So that is going to kind of take place, especially with like our smaller currents and the things that so this is only some of our currents, right? So we have lots and lots of smaller currents that are going to be happening that are just not shown on here. Cool. Okay. And also this is the Intertropical Convergence Zone, this red line here. And if you've never heard about this, it is a very important and really cool part of the Earth. So the Intertropical is going to be a band of perpetual thunderstorms. So it's basically just going to have, it's basically just going to be thunderstorms like year round, which is super interesting to think about. And so that's going to affect, obviously, the climate in these regions. So if you think about like your rainforests and things, those are going to be happening kind of in these regions. And so those perpetual thunderstorms are going to affect our hurricanes a little bit as well. So we'll get into more detail on that in a second. So then we also have the Coriolis effect, and the Coriolis effect is going to be changing our water movement as well. So the Coriolis effect is going to be pretty much the water and the air's response to the rotation of the Earth and to the shape of the Earth. So if you think about the world, right, our lovely world that we live on, it is the shape of a sphere. And so this sphere is rotating, right, on an axis. So it's kind of more like this. And it is spinning. And as it is spinning, this part of the world, the equator, or that part of a sphere, any sphere, is going to be the widest part. And so this wide part is going to basically be rotating faster than the pole parts. So if these are your poles right here, because this is so wide, it's going to be rotating a lot faster than these two parts here. And so that is going to cause a change in direction of anything like water or wind, anything that is moving at trying to cover like miles and miles and miles of distance, right? A long distance. So your Coriolis effect is going to basically create things it's going to cause things to go to the right in the northern hemisphere, and then it's going to cause things to go to the left in the southern hemisphere. And so that's going to affect our hurricanes as well. So here's just a quick glimpse at what's happening whenever we have hurricanes. So, you know, here's a poll for which way do hurricanes rotate in the Gulf of Mexico. So I'm going to talk a little bit about this, but go ahead and give me your clockwise or counterclockwise. Okay, so most of you put clockwise, so they're going to be rotating counterclockwise, and I'll talk about why in a second. So this is what you would traditionally imagine whenever you think of a hurricane, right? This isn't a real hurricane. This was just kind of like a simulation done with models. It's very large. So what a hurricane is formed by is going to be a low pressure system, and it needs warm water to be energized, right? So that low pressure system in the world, basically everything in science wants to be in balance, right? So if you have a low pressure system and high pressure systems, they're going to try, all those high pressure systems are going to move towards the low pressure to try to even out. And so what's happening here is you have a low pressure system, and then all these high pressure systems on the outside are going to try to come into that low pressure system. But because of the Coriolis effect, as those winds are moving inward, since they're moving at such a long distance, they're going to be deflected because of the rotation of the Earth. And so remember I told you that the winds are going to be named based off of where they're coming from. So if you were the wind in this image right here, these white arrows are the wind. So if you were the wind, you're getting deflected to the right. And you're trying to get into the eye of the storm, which is that low pressure system. So all these high pressure systems that are coming in are getting deflected to the right. And all of those right ways, deflections, are creating this rotation that is going to be happening. And so in the northern hemisphere, it's going to rotate counterclockwise because everything's going to the right. And then in the southern hemisphere, everything is going to be deflected to the left. And so it's going to create a clockwise rotation. So in the southern hemisphere, you're going to have things, they're called like cyclones and typhoons. It's pretty much the same storm as a hurricane, right? The same process of things happening, right? The low pressure system, all the high pressure trying to get into the middle, you have storm surge, you have high winds, you have that rotation, right? But it's just going to be rotating in the opposite direction. People always talk about, do the toilets flush? Answer to that is no. They're not traveling far enough. They're not going out a far enough distance to change. And also it has to do with the engineering of the toilet. So there's your image. There's the eye of the storm. There's also a part of the storm called the eye wall, which is basically, it's the strongest part of the storm, but that part is going to be where that counterclockwise rotation is going to be the most compact. So it's usually like going to be like right here on a hurricane, because all of those counterclockwise movements are basically like congregating right there, boom, and so you get the eye wall. So that's where it's going to be the windiest. And then once you get into the eye of the storm, it's really nice and pleasant, but just for a little while, right? So the path that our hurricanes are going to follow are going to be directly affiliated with the currents. So we have this current here. This is the same map we were looking at earlier. I just isolated the ones that we're looking at, the ones that matter for hurricanes. So you get all of your winds coming off of the coast of Africa. And so that's what's going to create a lot of the power for our storms. It's going to initiate a lot of things. This is also right where our ITCZ was, right? So this was those perpetual thunderstorms. So you have all these nice, lovely winds coming, and you have these nice thunderstorms that hang out right there. And then you also have these currents. And so these currents are going to move that water. They're also warm water currents, right? So that they have the red arrows. And so they're going to move all of that thunderstorm weather and then the wind and that warm water. And that's basically what is going to start your hurricanes. It's all the perfect ingredients, right? So all of that was going to move closer to the Gulf of Mexico, and then it can, come up into the Caribbean and then eventually make its way to us. So what happens when the hurricanes get to us? So that means we have to talk a little bit about the loop current. So the loop current is a flow of warm water that travels through the Gulf of Mexico, past the Florida Keys, and up into the Atlantic seaboard. So this warm water is going to be traveling from the Caribbean and up into the Gulf. So it's variable in that sometimes the water travels all the way up to Louisiana, and other times it barely makes it into the Gulf before returning to the Atlantic Ocean. So the loop current is going to have a big impact on our hurricanes. It's also going to here is a close-up image of what the process of the loop current looks like. So this is the Gulf of Mexico right here. And so your loop current is going to come in right here between Mexico and your Caribbean. And it's just going to kind of turn around and come back up. And this turns into the Gulf Stream right here. So this is warm water, right? And if you look here, you have warm core eddies and then you have cold core eddies. So this is going to be pretty much like little pockets of water that are going to be rotating differently from each other. And then they're also going to be different temperatures. So the warm core eddies, if you remember way back in the beginning of this lesson, we talked about the density of water. So warm water is less dense and cold water is more dense. So warm water has those molecules that are going to be farther apart, right? And then cold water has those molecules that are going to be closer together. So because of that, the ocean kind of has like a bunch of little pimples if you think about it, because the warm core eddies, since all those molecules are farther apart, they're going to sit higher up than the cold core eddies. So it would be like if I had I have this here squirt bottle and I have this here speaker. So they're going to be sitting at different levels. And whenever you look at that from the top, the warm water is going to be up higher and your cold water is going to be down lower. So that is just what is creating these eddies. And so when hurricanes come in, they can get really powered by those warm core eddies that are just sitting up real nice and high. They're already rotating. And so that warm core eddy is just going to pretty much energize the hurricane as it sits there, and it's just going to strengthen it. Also some changes with our loop current. Sometimes the loop current's coming all the way up here. Sometimes it's really not. And basically as the loop current gets faster, this part here will kind of pinch off and create an eddy. And then the current itself will pretty much just come like this and then go back up to the Gulf Stream. So that just varies with time. So over certain years, it'll be, very prominent, and other years it won't. So I have some exciting resources to look at as well. But just any questions about any of this information, like our ITCZ, or our hurricanes in general. I don't know if y'all can see everything that's popping up on my screen, but there's a lot happening on this side. So I do have this, which is basically like just a little at-home experiment that you can do using vegetable oil and then also thyme, like the herb, or I used parsley, I think. But this experiment will illustrate the global conveyor belt. So if you have these like coffee mugs, that's what this is. It's just some coffee mugs stacked up and then a casserole dish and a whole bunch of oil. So when I did this, I used olive oil and it was not as successful. So I would definitely recommend using the vegetable oil. So the flakes of thyme are sprinkled into the oil and kind of all mixed together. And then you put a candle beneath your dish, and the center of the oil will start to heat up. And so then you'll be able to watch the all of the thyme or the parsley move, and that's going to kind of simulate the global conveyor belt. Yeah, any questions? Do we have any questions about any of this information that we've talked about? Our first guest speaker for the week, can hurricanes make cold water warm? That is a great question. So hurricanes can kind of move water, but they're not going to be the source of heat. So they are not themselves going to make water warmer. They are going to be using that warm water to create that movement and to start the rotation. So they aren't going to be making any water any warmer. They're going to be using the warm water, but they can push water. So they can be changing the temperature of water by moving it somewhere else. But that's not them themselves creating that heat. Good question, though. Last week we had a question about can cold water, why can't cold water be the source of energy for a hurricane? So I use the example of like if you're thinking about if you're thinking about ice, for example, ice is going to be that water that all the molecules have pretty much stopped moving. And that's why it becomes a solid, because they're no longer fluid, right? So those molecules just kind of stop moving and they're basically suspended. And so warm water, once you're starting to heat water up, like if you imagine boiling water, the molecules are moving very, very, very quickly, and then they are turning into water vapor. And so that's, or steam, right? And so that fast moving water, that is pretty much just energy, right? Because there's so much heat in it that the heat is trying to escape. And so if you want something to have energy, usually you would apply heat, because the heat is the energy. So that's why cold water cannot be used to create a hurricane, because it's lacking the energy that it needs. It's very slow moving water molecules. Any other questions? All right, well, our speaker at 3 p.m. Is Dr. Kemal. He received his master's and his PhD at the Georgia Institute of Technology in civil engineering with an emphasis in coastal engineering and a minor in oceanography. He's been an assistant professor in the ocean engineering program for a little less than 2 years at USM. Before he was a research scientist in the Division of Marine Science at USM, and worked at the Naval Research Laboratory as a contractor. So his fields of study are coastal ocean modeling, coastal engineering, ocean engineering, and physical oceanography. So today he's going to be talking to us about forecasting the dynamics of our oceans. So coastal ocean modeling applications in physical oceanography and ocean engineering. So he's going to be talking a little bit kind of about like our, basically how we forecast the weather, how we are able to predict what's going to happen with the weather, basically predicting what's going to happen with the ocean in like, you know, what are the currents going to be doing in the next few days. So he works with a lot of models and is able to kind of show you what that process looks like of how they figure that out. So it's super, super cool. Thank you for joining us virtually today. Thank you for coming to Blue Planet Week 2. If you have any questions or anything that you would like to share with us, you can email us at marine.education@usm.edu. If you do that at-home experiment, please take a picture of it and send it to our Instagram or post it on Facebook and tag us in it. And yeah, hopefully we can share it on our page. So let us know. And if you would like the link to that at-home experiment, you can take a screenshot of this slide, or you can also copy and paste it. If they can put it in the chat box for you, then that'd be great. All right, but if there aren't any questions, I will go ahead and sign off. So thank you so much for joining us, and we will see you at 3 p.m. today with Dr. Kemal. Welcome back to Blue Planet. So see some of y'all hopping on. Excited to see you. So I, Apollo, Connor, Denver, Isabella, Ryan, Sadie. Hi. Thank you so much for joining us. Hopefully we won't have any of the audio problems that we had in the last session. So if you were here with us for Hi Sims for 1 o'clock, I had some technical difficulties, as they say. And I think they were all on my specific computer. So hopefully we won't have any more of those issues. I did the traditional turn it off and back on. So let's hope it worked. But thank you all for coming to Blue Planet. So today we talked about physical oceanography a little bit, and we had some new information presented to you, hopefully, about some hurricanes and currents. And then we talked about Coriolis Effect and the Ecumene Spiral a little bit. And so today we have with us Dr. Kemal. He works with the University of Southern Mississippi in the Marine Science Department. And so he works with forecasting currents pretty much. And so he is with us here today. So he's going to give us a presentation. So without further ado, let's hear from Dr. Kemal.
All right. Thank you very much. Hi, everyone. Well, I wish we were at the MEC campus today, you know, be in the same room, talk face-to-face, interact with each other. But unfortunately, due to the current COVID-19 situation, we're exploring new ways to communicate with each other. So hopefully it will go along well with no technical interruptions or issues. I am Dr. Kemal Cambazoglu. I am an assistant professor at the Division of Marine Science in the School of Ocean Science and Engineering at USM. And let me share my screen PowerPoint file with you real quick. So what I have for you today is a presentation that mainly talks, you know, about my experience, my research, my background, the link with physical oceanography, as well as ocean engineering, and the work that we are doing at USM, the exciting projects that we are working on. So I'm sure you had a great session at 1 p.m. already. You know, you talked a lot about physical oceanography and the dynamics of our oceans. So I will touch on some of the concepts that you have already heard and learned about, and also, you know, expand beyond. So please feel free to ask any questions using the chat box, any question that comes into your mind. as I speak if you want, and then we can address them at the end. So without further ado, again, this is MEC as the background of my choice for the title slide. So the title of this presentation I chose is Forecasting Dynamics of Our Oceans. And I will mainly talk about coastal ocean modeling applications in physical oceanography, as well as ocean engineering. I do teach in the ocean engineering program at the University of Southern Mississippi, and I also, work mainly with the physical oceanographers within the Division of Marine Science. To start off, I want to give you a quick background of the road that led me, from the beginning, which is after high school. That's the reference point here, and up until now. So I had a bachelor's and master's at METU in Turkey. I'm a Turkish American, and with an emphasis in hydromechanics. I grew up, by the Aegean Sea, and I always loved the blue water, the seas, the oceans, the straits, and so on and so forth, as well as rivers. And that led me, as I go through my bachelor's in the senior year, to hydraulics and hydromechanics, to fluid mechanics, and to work with water and the dynamics of flows, water flow mainly. Then I did my PhD at Georgia Institute of Technology in Atlanta and Savannah, Georgia. Both Georgia Tech had a campus at Savannah. We had our boats there. We would go out to the field. We would survey the beach, the bathymetry of the beach, and so we had lots of hands-on activities, as well as my main focus, my dissertation work was on modeling the oceans, the dynamic of the ocean, which I'm going to talk about in the upcoming slides. So again, there, my PhD as well as master's, this time had a focus on coastal engineering, still in civil engineering, but I also had a minor in oceanography. Then I took a position at NRL here at Stennis Space Center, the US Naval Research Laboratory, and did a postdoctoral research there. The Naval Research Lab has its oceanography division at Stennis Space Center, and I work particularly within the ocean dynamics and prediction branch there, and work with the scientists there. Stennis is one of the most concentrated campuses in the world with oceanographers. So the highest concentration of oceanographers, maybe I should put it that way, in the world is known to be at Stennis Space Center, actually. Although it's a NASA facility, and it may be well known in the area for shuttle rocket engine tests and its events. So actually, my work at NRL also led me to an official position at USM as a research scientist. So I was a contractor at NRL, and I transitioned to USM afterwards, and especially for the Concord project. It's the Consortium for Coastal River-Dominated Ecosystems project, which was funded after the BP Horizon, Deepwater Horizon oil spill, actually. So, and then another project, again, with those funds dedicated by, BP oil spill funds on the oyster restoration. And then a couple of years ago, 3 years ago to be exact, USM has decided to open up a new program in ocean engineering, which was fantastic news for me. I was very excited and I applied, and I was lucky to become one of the assistant professors, in this great program that we have now. All right, so normally what I do with PowerPoint presentations is I prefer not to, put in, all the information like a blurb like this, but use animations. But, I tried I started doing that, but then I hesitated doing it because of the remote setting, and it's not a local computer, and we're not in a room, you're not looking at a screen. So I had limited animations because of that, and most of my slides will have lots of information feed to you at an instant, but I'll try to guide you, and I should turn on the laser pointer to be able to guide you when needed. So the title of the presentation had the word forecasting, right? And if you take a second and if you think what comes to your mind when you hear the word forecasting, more than likely it will be weather forecasting, right? So it happens every day. We can turn our TVs every evening and hear about the weather forecast for the next day. So forecasting has been done for a while now, and it is mainly a prediction of conditions at a location and at a given time, right? And mostly a time in the future. And sometimes we, well, not sometimes, very often we actually look back in time as well, and that we call timecast, actually, not forecast. So here's an example, a very recent example. This is tropical storm Cristobal that actually came through our area. And whenever these storms come, we actually keep an eye on them, right? Even when they are far from us. I sometimes keep an eye on, bigger storms that form right by the African coast and travel all the way across the Atlantic and come Caribbean, enter Gulf of Mexico and whatnot. So, and that's weeks and weeks long of a process actually from the start. But when it gets closer and closer, of course, then we start relying on shorter term forecasts. So here actually you see multiple days, Cristobal over the Yucatan Peninsula, and a forecast on where it is predicted to go. And then at pretty much, at the center of Gulf of Mexico, where it's expected to go, and here right by the landfall. Now, what happens is, when you do these forecasts, you rely on models. And that first numerical weather forecast that I talked about was performed in 1950. And at that time, they used a supercomputer, used the numerical modeling system that actually modeled the atmospheric dynamics, of course, for a weather forecast. And they did a 24-hour forecast, and on that supercomputer of the time, it took 24 hours for the computation. So basically, the computation happened over the time that it is trying to solve for the forecast, which is, of course, undesirable. Now, if you use the same computer model of that time on the chip of a cell phone, of your cell phone, today, it will actually take less than a second. So that tells you about how technology advances, over time, of course. And that's quite a bit of time. And this chart here actually shows, how it changed from 1950 coming to the day of the, manuscript that I took the chart from. And now we are talking, when they talk about the speed of these, supercomputers and their computational power and efficiency, they are talking about petaflops per second, which means within a second, these computers, systems are capable of doing 1 quadrillion computations. So that's what that means. So they are that powerful now. And again, like I said, we use numerical models or numerical modeling systems, right? And there are a lot of them. So here, if you look at these two charts, what you can see is if different models are used, what the storm tracks are expected to be and what the storm intensity would be over a almost a week-long forecast here. So as you can see, there are differences. All these models have different dynamics embedded in it, different mathematics, different physics you can think of, and different way of representing the reality. In the end, they are trying to mimic the reality. And some of them, do a great job. Some of them, sometimes perform great, sometimes cannot. So because they have limitations, and they can be, they can perform, better under different conditions, and so on and so forth. So you have to take the results with a grain of salt, of course, and keep that in mind that it's a model, and it won't be, you will always shoot for accuracy, as a high accuracy, if possible, when possible. So the goal is to simulate the dynamics of the ocean by this numerical model solution. And it's really like a simulation of reality, which in this case, I have two GIFs here. One of them showing you the ocean salinity, sea surface salinity and currents. And the other one is showing water temperature and currents at 200-meter depth. So in oceanography, the goal of using these numerical model solutions is to use and solve complex mathematical equations, and that actually represent the physical principles, that define these dynamics. And from your physics courses, you know that it all dates back to Isaac Newton. We could tell, and but of course it gets more and more complicated. I actually have lots of equations in the slide which I removed, not to scare you off of physics or mathematics. So, but these are really, long lines of codes basically that is written to solve actually really conservation of mass, momentum, energy equations that define the mechanics and dynamics of water, of our fluid in this case, or for atmospheric dynamics, air, of course. So, and then you are looking to solve for different oceanographic variables, temperature, salinity, both of which define the water density, currents, waves, tides, winds, and generally looking at the ocean circulation, the transport of particles, water masses, if it's a spill and oil, if it's oysters that you are looking at, transport of oyster larvae, and exchange of waters in between different water masses. Estuarine waters here in Mississippi Sound will be different than the shelf waters over the continental shelf, which will be different than the deep water, as you go deeper off of the shelf break and so on and so forth. So there's always an exchange going on as well. So, like I said, supercomputers have been used since 1950s, right? So to solve these equations computationally, to model the dynamics, and supercomputers are used for many different purposes in science, engineering, medicine, and so on and so forth. With a computer model, you can actually also model, how our hearts are pumping, for example, in medicine. And in our case, we, of course, model the oceans. Here in this case, in this plot, you see an unstructured grid that is used to model, the flow over, this is half of Atlantic, the Caribbean, and Gulf of Mexico. This particular one was intended to study tides, actually. So now the solution is over a predefined computational grid, be it an unstructured grid like here, or sometimes structured grids. By structured grid, what I mean is you actually make computations on nodes at different locations. And if you look at this 3D cube at, every node there, every point there, you can think of computations are happening over the horizontal in X and Y directions, or over the vertical as well, over depth. So in a structured grid, usually, these are even spacings in horizontal and vertical. In an unstructured grid, it's not even spaces. It's actually not squares like this or rectangles like this, but it's triangles instead. And you see how, all these coastline zones are black all across. And that's because the size of those triangles gets smaller and smaller and smaller. So it could be here 10 kilometers, for the edge of a triangle. And right by the coastline here, it's going to be less than 10 meters. So it's going to be really high resolution. Having a solution for a variable 10 meters apart, less than 10 meters apart from each other. In order to do this, high-level computer programming is required, be it in different computer languages, some of these, that I put here. And also, it will require parallel computing, which means hundreds or thousands of processors are going to be used simultaneously. So, so they will all be working together, exchanging information in between and so on and so forth. So these are really powerful systems. And interestingly enough, more than one of these powerful systems is in our state of Mississippi. US Navy has its, high performance computing system at Stennis Space Center, actually. It's called Navy DSRC. And the computing systems, each of these are, examples, 3 of those computing systems, and they get their names from astronauts since, Stennis is a NASA facility. So, and these computers, they get upgraded over time, they get replaced and their names change. Recently, one of the, computers that I hopped on for simulations, was named Armstrong, for example. So, and the Army, by the way, US Army Corps of Engineers has its Engineer Research and Development Center in Vicksburg, Mississippi, and they have their supercomputing system there. We visited them, a few years ago. These are fantastic, facilities. They're all cooled, of course. You can think of all these processors working together. Is heating a room up, so they're within really, nice cooled rooms and so on and so forth. So now there are, as I said earlier, different models for different purposes, and there are wave models, there are atmospheric models, there are ocean circulation models that solve for the currents and temperature and salinity. And there are sediment transport models that we could use to look at how things change on our beaches. And there are biogeochemical ecosystem models, which are actually looking at interactions in between physics and biology and geology and chemistry of our oceans. So in the end, the best solution is actually a coupled modeling system where these pieces come together, communicate with each other, exchange variables in between to have a more accurate solution, of the dynamics of our oceans. And they are designed for different, problems, include different physics, have different resolutions, have varying model performances. So sometimes you can choose one over another because you know that it performs better for a particular scenario, and so on and so forth. And as I spoke, lots of names appeared on the screen. These are just some examples of the models existing out there that have been developed by many, well-known scientists, really hardworking, acclaimed engineers and scientists in our field of study. So I will talk about a few of these models today because we do have a lab at Stennis in our USM Division of Marine Science facility, which is called the Ocean Weather Lab. So this lab is intended to actually pull information from existing model runs that not necessarily has been done by us, but these different groups are doing model simulations of Gulf of Mexico, but it is really geared toward Gulf of Mexico. So we pull model information as well as satellite information. So because satellites pass over Gulf of Mexico, particularly a few satellites go over Gulf of Mexico once or twice a day, every day, and take a snapshot. And with different sensors on those satellites, you can actually extract information about ocean temperature, ocean salinity, particles, within the Gulf of Mexico waters, or larger fields that's covered by the satellite snapshot. So what we do at the Ocean Weather Lab is we pull in this information, and here are some of the variables that come from ocean model products versus satellite products. Chlorophyll A, which is an indicator of the amount of plankton in water. Particle backscattering, which is an indicator of let's say sediments in the water. So river plumes bring in a lot of sediments when freshwater diversions, like Bonnicary spillway in our area is used. That brings in a lot of sediment into the estuarine system and shelf waters, of course. Sea surface temperature is another one. And when it comes to ocean model products, I have some figures. We use Google Earth to bring in data together so that it's easier to navigate around, look at different areas in the Gulf, to look at larger dynamics like the loop current, or not only to the Mississippi Bight area that you see here, which is mainly composed of Louisiana, Mississippi, Alabama, and Florida waters, but sometimes look at the Louisiana-Texas shelf to the other side of Mississippi River Delta here, and put different products on top of each other. Here, currents are overlaid over temperature. Here, salinity, currents are overlaid over salinity. We can take cruise tracks. Here you can see, lines, black lines that were actually cruise tracks of Point Sur, when one of our research cruise campaigns happened back in 2016. The yellow line here is the track of a glider, for example. So you can, put a lot of information on top of each other. And we can also look at the vertical structure, variation of temperature and salinity over the water column. So here you can see, the shelf break, how, the water gets deeper actually, and the top 100 meter of the water column. And you can see, for example, a river plume here, because this low salinity denotes a river plume. In the salinity diagram, you can see how higher, much higher the salinity is, deeper or farther offshore. So these are some variables, and the goal is to synthesize all these products to understand, investigate, study the dynamics of our oceans for different projects that we are working on, of course. Now, two particular models that I put on this slide is the Navy Coastal Ocean model, which is used by NRL actually, and the model that we developed for the Concord project. Here you see the domain of it. So this box is the domain of our model, and the computations cover the study area basically. And I'm not going to go over all these details, but what I'm going to tell you is in this modeling system, these two models actually talk to each other. ANCOM is a model that is coarser resolution, but it covers the entire Gulf of Mexico. So it can capture the dynamics of the loop current, impact of loop current, on our study area, for example, and, the larger dynamics happening. And the Concord model is higher resolution, it's 400 meter resolution, then it can, capture the barrier island inlet dynamics better. And, because of its higher resolution, it can provide a better solution within the estuarine system, which you will see why we use such a system for our studies because of our project. because the focus is on estuarine systems and coastal ocean. So we're looking at the physical oceanography and the dynamics within these shallow water environments and the exchange between shelf waters and estuarine waters. That's why, we need this higher resolution. We are actually currently working on even higher resolution which we call nested grids. So we are actually nesting other grids into this one. Actually, we expanded this one to capture the entire Lake Pontchartrain, and nesting a couple of more grids to drop the resolution down to about 40 meters, so even higher resolution. Now, you may have already talked about this, but we actually have research vessels. Our largest research vessel right now is Pointer. And here you can see the Pointer for an unmanned maritime systems certification course, cruise, because all the yellow vehicles that you can see here on the deck there, they are autonomous vehicles. One is called Eagle Ray, it's the bigger one. The other one is called Mola Mola. And, these autonomous vehicles have different purposes. Rich Delgado is going to talk about, these on Wednesday, I think, and he's going to provide you with more information. But what we do is when these research campaigns happen with these vessels, most of the time, we actually work with the scientific crews on the vessels, and if I'm on, part of the crew on the vessel, we work with, our colleagues on land that provide us with this model information, satellite information, and so that the cruise, it could be an informed cruise, which I'm going to talk about in a few slides. And I'm happy to say that USM and LUMCON, the Louisiana University's Marine Consortium, I think, will jointly operate a regional class research vessel funded by the National Science Foundation. It's going to be, the biggest research vessel that is dedicated to the Gulf of Mexico and Caribbean. It has been named after the civil rights activist Gilbert Mason. So, like I said, we provide information to these vessels, right? And here are some examples on how we do it. So, before cruises, they give us their anticipated cruise tracks. And sometimes it's really, there's a plan. Like Pointer is going to go out from Gulfport, go out. This is Ship Island there. And then it's going to navigate towards Mobile Bay. And then it's going to do a transect, right? And then it's going to come back and then do another transect closer to Chandelier Islands. This was a cruise plan that is known ahead of time. So whenever this vessel was leaving, it was known that on day one, it's going to do this. On day two, it's going to do that, and so on and so forth. There's more, of course. But so with ocean model forecasts, you can predict what's going to happen within the next 24 or 48 hours, right? Or even more, of course. But it's more reliable for the first 24 hours span rather than a week from now. So you provide that information to assist with measurement activities during pre-cruise planning and as well as during the cruises. So all these are processed and prepared daily and sent out or shared, through a shared folder platform with the vessels so that they can take a look, at any time to see how dynamics are predicted. This comes in very handy, a lot of times because although there are pre-planned, cruise tracks, conditions change, conditions, sometimes get rough, or if you're, planning to detect a certain feature, that the location of that feature, for example, the Mississippi River Plume here, might change over time. So it is important to have a well-informed understanding of the dynamics and make decisions accordingly. And this is an example of how we did it. We received a call during the summer cruise of the Concord campaign from the vessel. And they said, you know, they were working on the model day Plume. And they happened to go out of the Plume and then work on something else. And they wanted to go back into the Plume. And they said, hey, could you provide us with model predictions and how the Plume changed over time? So that we can go back into it. So this is exactly what we did. So even if I show here like 6 hourly or 12 hourly actually variation, we worked on like hourly variation of the Plume, sent the information to them, and we actually received another call and they were like, hey, we're back into the Plume, thank you. So it is, you know, really this working relationship, you know, towards adaptive sampling that makes our, you know, research efforts more and more valuable. So here's the loop current, and I know you talked about this, and what is important about the loop current is, yes, when a hurricane is coming, we hear a lot about the strength and intensity and the track of the hurricane, which is mainly that information comes from atmospheric modeling, right? Or satellite imagery, or actually information that's coming from field data collected from the field, right? But it is important also to understand the interaction between the ocean and atmosphere, because here in this example, in this chart, we do have Hurricane Katrina and the track of it and the intensity of it. Here you can see maximum winds in miles per hour at different locations, right? So what you can see here is coming off of the coast of Florida, Hurricane Katrina had 75, 90, 100 miles per hour winds. Of course, you know, it had weakened going over the land there, and it was intensifying again. So what's important to understand here is then it started to go over the loop current. And the loop current contains warm waters in it. So as you can see in this temperature, as you can see in this water temperature plot, or even if it's a different time, you can see how loop current contains warmer waters. And this is the sea surface height actually. And then going over those warm waters, Katrina started intensifying. It exceeded 173 miles per hour in strength. So it was a massive storm covering most of, you know, northern Gulf of Mexico. It hit our coast. So while we are predicting, you know, such a storm, it is important what feedback is provided from an ocean model back to the atmospheric model, because it is that feedback and that sea surface temperature information that will allow the atmospheric model to have a more accurate solution and prediction and forecast in general. So this is why ocean modeling could become really crucial in situations like this, or in Deepwater Horizon spill. Where did that oil go? You know, coming out of from the bottom of the ocean, having underwater plumes spreading out, coming to the surface, where would it go over time, and so on and so forth. So these kind of problems benefit from ocean modeling, as the information coming from ocean models is crucial. Now, characterization of a plume, like I said, was a goal of the Concord project. And the Mississippi River plume, here you can see, and the Mobile Bay plume was targeted during these studies. And this is a model solution of salinity, which is salinity could be, you know, much lower than 30 there, but, you know, basically coastal salinity was capped off at 30. That's why you see all these coastal waters in dark blue with their salinity. But you can see how it spreads out, and while it's mixing, you know, salinity reduces, so that plume, of course, you know, as it disperses, you know, diffusion and mixing happens. So it mixes with high salinity waters, and you can see the signature of Mississippi River plume as well as the Mobile Bay plume going out there. And sometimes Mississippi River plume gets captured by the currents of the loop current, and then it can make its way all the way to Florida Straits, really. It can be transported far distances like that. So now here are slices with our modeling system. We can look at transects. So this is a transect that you can see here. So you can see low salinity waters near the coastline there. And this portion here, it's the Mississippi River plume crossing the transect there. And it's actually widening, as you can see, and covering a larger area along the transect. And this is looking at the Mobile Bay plume. This is the other transect. So why is this important? Because both of these river plumes bring in large quantities of fresh water into the system, as well as nutrients and sediments into the system. And that fuels, the marine life, of course, the planktons, the fisheries, it changes stratification, it basically makes the waters more and more productive. And that's why for the whole ecosystem dynamics, it's crucial to understand these plume dynamics. And we had multiple different ways other than the models of looking at this. In addition, working together with the models, let me say. And field work is a significant component of this. Like I said, we have research cruises with Pointer and other vessels. And this is a small boat study. This is our colleague, Steve Dykstra from Dauphin Island Sea Lab, actually, deploying a drifter. So this is what we call a drifter. It's got a GPS there. It communicates with a satellite at all times. And with the near water surface currents, this drifter actually, as the name stands, this device drifts around. And here in this plot, all the black lines are different drifter tracks over time. And here in this one as well. And the gray lines are for the same drifter releases, the model predictions. So you can see the model is sometimes doing a great job. Sometimes, it diverts from what actually happened in reality. And it is our goal to understand why those diversions happen, how the model is capable of capturing the dynamics. And like, for example, here, this drifter gets caught, in this oscillation there and makes the loop. The model does that, but of course it's off, you see, it's not right on the actual drifter track. Then we are trying to understand, okay, the model captures the dynamics, the drifter in the model does the same movement pattern, but it's off, and why it is off. That is what we are trying to accomplish to improve our models. Another device that we work together with here in this case is a glider. This is an ocean glider. You'll hear more on Wednesday about this. An ocean glider does not have a propeller and an engine in the back. It's got a battery inside, but the battery mainly powers the sensors and instruments within the glider body. The glider actually moves around by changing its buoyancy. So you can think of this as it sucks in water to increase weight, starts going down, and then pushes that water out, decreases its weight, changes its buoyancy, and then goes back up. So it does these zigzags as it goes along the way. It gets piloted, actually. These gliders, they communicate when they come back up at the surface. As you see, it puts its tail up, and then it communicates with a satellite. So someone can change the track of the glider or the mission. If it was looking at from surface to bottom, maybe there may be a reason to look at a certain depth difference, certain depth zone, let me say. So this is that glider's track. It actually came all the way down. It was, its track was intended to go over the stations. You see 5 pins there. Those were actually mooring stations. And this is along that track, the data that it collected. This is the temperature data, seawater temperature. So this is from the beginning till the end, the temperature along the track. Actually, this area where, depth is more than 120, the plot is top 120 meters. This is where, it made that turn. So it went actually deeper than 120 and started, going back over those stations, which were roughly 45 to 60 meters depth. So with the model, what we can do is, this is the model prediction or solution, let me say, in this case, because it was not, it's not a forecast per se for the future. It's for the, past in this case. So these 5 are those 5 stations, temperature variation over those 5 stations. And if you compare the two, you can actually see similarities, how, there was this warm water that glider went through, and then, there was an event and the, cool water zone there, and then again, a warm water. And these oscillations were also, somewhat captured by the model, which is actually crucial and important because those were representative of internal waves that happen. Those are not like the waves, that happens at the surface, but those are waves that happen underneath the water surface. So, and those 5 stations, all of those 5 stations had a mooring, and they had a current profiler at the bottom, as well as, they had a mooring line with instruments attached to it. So we were able to capture the salinity and temperature variations, as well as other turbulence measurements over the water column at all those 5 stations over time, basically. And here on the left, temperature and salinity of those 5 stations. Here on the right, the model solution for those 5 stations. And again, you can see how well the model is doing in capturing, the salinity versus the temperature over that collection time. And as I said, we pull in satellite and model information together, right? So the beauty of this is you can actually put model and satellite solution side by side and see how both of them, the sea surface temperature is changing in time, and how well the model is doing, again, to capture the dynamics. It's actually, there was this warm week in October, and then, a frontal event happened and the waters cooled off, significantly within a 2-day period. And you can see how, this was captured in satellite here, and the model mimicked, of course, the same solution. All the white spaces in the satellite imagery are clouds. So that is one disadvantage of satellite imagery. On a cloudy day, you won't get any data, unfortunately. And that's why these dates, 11, 12, 14, 15, so there are gaps, because 13th of October was quite cloudy. There was no satellite data, or the same with 17th, and so on and so forth. Now, with this, you can look at, this is the same October time period. You can look at understanding how shelf waters actually get into the estuarine system, how those high salinity, high temperature waters with the current patterns in the area affect, the estuarine waters. So ocean modeling combined with measurements help us understand such processes. We actually published a paper in the Science Teacher journal. It was on developing a lesson, a course to study oceanography, and we called it virtual oceanography, because in this case, what we did is, relying on ocean model and satellite imagery products, we said, you know, you can be the chief scientist of a Pointer cruise. And if, for example, in this case, you wanted to study the dynamics of the Mississippi River plume using Google Earth or ArcGIS, you actually can build your cruise plan. So, of course, satellite imagery is daily and it's a snapshot. So it's not a forecast or prediction. So to plan your cruise, you can rely on the model product. Here, this is the Mississippi River plume going south, the model says. So you can say, Pointer leaves Gulfport, goes out to the shelf, comes down, captures the plume, or, you know, all these pins are stations, and then come back. And this is what happened in reality, actually, during the cruise time. So you can see, you know, if you planned on the model product, you actually had a pretty accurate and meaningful cruise plan, as the reality shows. But what you can do is, what happens, this is a, let's say, 2-day, 3-day cruise, right? Of course, satellite information will come in, and you'll see how, you know, there will be similarities and differences between the model solution and reality. For example, the plume is somewhat off, even if it's going south, it's farther east than expected in the model. So then you can adjust accordingly. Maybe, you know, Pointer keeps measuring as, you know, as it streams, and then you will see actually that you go into the plume and then come out of the plume. Maybe you don't have to go all the way out to that station. You can cut it short to save time, so you can adapt. Another study, like I said earlier, that we have is, and I'm wrapping up really shortly, is an Oyster Study. Here, what we did is, these are, I think, 18 oyster reef locations within Louisiana, Mississippi, Alabama waters. And using the model, the Concord model that we have, we actually put in drifters, virtual drifters that represent oyster larvae coming out off of these reefs. And then you can see how those drifters, where do they go? Like some of them go out on the shelf. The color denotes time. And this is a 30-day simulation. So as it goes from blue to red, you know, it shows, you know, on what day from the beginning that the drifter is at. So the goal here is to understand actually the connectivity between these different state waters and the reefs in between different state waters. And also over these oyster larvae pathways of transport, how does temperature and salinity impact the oyster larvae and its potential success, or let's say survivability? Because oysters cannot resist low salinities, for example, and we provide the physical model output into a habitat suitability model, and we work with a biological oceanographer actually who uses the habitat suitability model. And the information that we provide him, not only temperature, salinity, but also you know, depth, sediments in the water column, and a few other variables that allows him to look at the basically suitability of the habitat, of the track that the oyster larvae takes on its success. So these are 3 scenarios in which actually in this scenario, you can see particles going from all the way from Mobile Bay to central Mississippi Sound. Here in this scenario, you can see particles coming out of Drum Bay, Louisiana, all the way into western Mississippi Sound and over the reefs there. So there could be connectivity in between reefs, larvae coming from other reefs actually settling and growing, you know, over the local reefs in Mississippi, or self-seeding scenarios that for 30 days, the oyster larvae just hangs around, you know, in the western Mississippi Sound over, you know, the actual originating spawning location. This could be combined with oil spill scenarios in this case, that we release a dye with a concentration within the model to, to see how, in this case, it mimicked, a pipeline, going over Mobile or Pascagoula, direction. If it erupted, what would happen, and so on and so forth. So you can, work with these kind of couple scenarios to look at the, larger, more complex dynamics. One of which is that affects the oyster habitats in our area is the opening of the Bonnicary Spillway. I have actually been reading a book called The Rising Tide, which talks about the Mississippi River and the Great Flood of 1927. And Bonnicary Spillway is a flood control structure that was actually constructed back in early 1930s. And it was because of that 1927 flood, which Mississippi River rose to a discharge of more than 3 million cubic feet per second at that time. So Bonnicary Spillway is the last line of defense, let me say, protecting New Orleans, but there are other, structures farther upstream, like the Morganza Spillway, that's at the Atchafalaya River, Mississippi River split, and so on and so forth. So when the discharge of Mississippi River exceeds a certain number, close to 1.5 million cubic feet per second, they operate the Bonnicary Spillway, which mainly diverts the Mississippi River water into Lake Pontchartrain through this floodway. I think this is maybe 7 kilometers long or something like that. So it's in between, it's a levee controlled area in which part of Mississippi River keeps flowing, of course, and about 200, 300 cubic feet per second gets diverted through these gated structure. Now what happens is that fresh water and the low salinity waters flowing into Lake Pontchartrain eventually comes out, makes its way through the Wrigley's Channel there into Lake Bourne and Mississippi Sound, and even all the way out to the shelf there. So unfortunately, this has a huge impact on the oyster beds here in this area by Bay San Luis. And in 2016, when Concord cruises were happening, actually Bonnicary Spillway got operated in January, which happened to be the earliest operation within a calendar year in January 2016. It had never opened as early as the month of January. And after 2016, it got operated in 2018, and then it got operated twice in 2019. The 2018-2019 back-to-back years was the first in its operational time since 1930s. And the twice operation in 2019 was the first that it got operated twice in a year. So which is telling a lot to us about climate change through the operation of an engineering structure, the frequency of operation of an engineering structure, I would say. So what we did is during the cruise, like I said, we provided information to the cruise because this was really an adaptive sampling cruise, looking at the dynamics in the area. And then in the 2019 opening, USM, crews went out, do a lot of sampling in Western and Central Mississippi Sound out on the field. And with satellite imagery and model products, we provided them with information during those efforts. And we are working in interpreting data, putting all the field measurements plus satellite imagery plus ocean model data together to understand. And like I said, we are expanding our modeling system now to include Lake Pontchartrain and the Bonnicary Spillway as well. So we are really gearing ourselves towards whenever future openings happen, we can do simulations. This helps us, through measurements, you can actually capture the temperature and salinity variations at different stations and locations that represent different water masses. As you can see, you know, these are different water masses of the Chandelier Sound there, of the, you know, Mississippi River Berthoud Delta waters there, as well as Mobile Bay waters there. And model products, both with currents, temperature, salinity, you know, predictions, as well as drifter predictions in this case, to look at if there was no spillway versus a spillway opening, how would the water particles, you know, spread out? So the transport and spread of fresh water could be represented by such studies. Now, the harmful algal blooms is another study, another thing that we can analyze with satellite imagery as well as ocean models. This is the Carenia brevis bloom is called the red tide, and this is a photo that shows why it's called the red tide. And this could be captured by different, you know, satellite sensors, the Modis Aqua, or the VIR sensor on Suomi. Suomi is a Finnish-American, you know, scientist who was known to be the father of satellite oceanography. Or meteorology, actually. So from satellite imagery, you can actually capture the bloom of this toxic, highly toxic algae. And with model results, you can actually, you know, look at how these blooms migrate over time from Florida waters to Mississippi, Alabama waters. Not very frequently it comes to Mississippi actually, and it goes mostly over to Alabama and then goes south, diverts south. But there are instances where, you know, it goes into the Mississippi Sound, and we, using the model products, try to understand and, you know, if we can forecast the future bloom events. Also, during Concord, we used another vehicle, which is a plankton imaging vehicle, as you can see here. So with a CTD cast, this goes down and captures temperature, salinity, fluorescence, chlorophyll. They actually captured a very thin layer of high chlorophyll or high fluorescence, which indicated a thin plankton layer. And then they actually, this was a Concord cruise, and this imaging sensor device was on. They went back to the location, and you can see here, this is an image from that imaging sensor, and these are actually planktons. And you can see, you know, a few planktons here and there below and above the thin layer. Here, it's a lot of planktons, mainly diatom chains. So we use the ocean model, try to understand what were the mechanisms generating this thin layer, how often it happens, you know, within the Gulf of Mexico. So I think I talked about this already. I'm going to skip this. This was looking at the shelf estuarine exchange, and I'm going to finalize with this, looking at hypoxia. Hypoxia happens in Gulf of Mexico, mainly in Louisiana, Texas, you know, shelf. On that side of Mississippi Berthoud Delta, but it happens in the Mississippi Bight as well. And, you know, we can use these high resolution ocean models that captures important dynamics like diurnal sea breeze. And then here you release a dye again with initial concentration 1, and then you see how it spreads over time. You can repeat these simulations over time and then understand, you know, how different water masses, how water masses can actually, you know, stay in a certain zone, which leads to hypoxic conditions. So we use model simulations like this to look at estuarine bloom dynamics, as well as to look at inner shelf, you know, implications of onset of hypoxia. Okay, so I'm again well over time. I apologize for that, but so in the end, I'm gonna just stop here talking about our research, and then I'm gonna remind you that at USM we have 3 unique undergraduate Bachelor of Science program, one in marine science, which is really a combined physical, chemical, geological, biological, oceanography, undergraduate program, one of only 16 in the nation. We have a marine science bachelor's degree with an emphasis in hydrography, which yesterday was World Hydrography Day. It's mainly, seafloor mapping with echo sounders, multi-beams, finding artifacts in seafloor, looking at the dynamics of the ocean bottom, let me say. And it is the only undergraduate program in the nation that provides a Category B certification that is approved by the International Hydrography Organization. And also we have this, as I said earlier, the new ocean engineering program, which is one of only 10 undergraduate ocean engineering programs in the nation. Ocean engineering program really is like a bridge in between engineering and science, of course, focusing on our oceans. So it is a very multidisciplinary program. And there are lots of career opportunities within Mississippi, as well as all across the nation, of course, if you pursued one of these programs. And with that, I will stop here. I talked a lot, and I will leave the floor to you for questions. And here, I put logos of some of the projects that I worked on and funding agencies, that help us continue exciting research every day. Thank you.
All right. Thank you for your presentation. That was very good. I love all those ocean models. So cool. So we have a couple questions for you.
Sure.
So usually, I know you said that you leave like the drifters out whenever you're working with the oysters. It said for 30 days for that one. But initially when you spoke about the drifters, they were being used for other things. So how long do you usually leave those out for, like current tracking and stuff?
So the current tracking ones were actually left out more than a week. Some of them actually eventually they make their way and they may hit a shoreline and you may have to go grab them. Some of them you can see they start wandering off, going further, southeast, and then you need to go capture them before they go all the way to Florida Straits. Right. Sometimes it's possible. So that's why the timing varies, but usually more than a week, between a week or two is the time frame. Sometimes it's even shorter, on the order of less than a week, of course. So so those were real drifters, deployed in water, and then since they report their locations through GPS, satellite communication, you actually with your boat go after it. So I think actually in one of those slides I had a photo of one that we went after using Pointer. So, and really the only hard thing was, when we were there, it was a sunny day. So everybody was out on the deck looking for this drifter. That's the drifter. It's a different kind of drifter, but it's got that orange buoy on top. So, and the satellite receiver transmitter was inside the orange buoy. So we were there with Pointer, and it had reported its location 5 minutes ago. I was reporting every 5 minutes. And everybody was out on deck looking for this drifter, and somebody saw it and pointed it out. Oh, there it is, And then we just went ahead and grabbed it with a hook. So the one in the model simulations that I showed you, they were, this is under our control. This could be 60-day tracking, 90-day tracking. We, with a control file, allowed these drifters, to be released at 18 different locations at actually 3 different depths, bottom, mid-water column surface. And then we said, we're going to track them for 30 days. So, and then we did the releases every day. So every day there was a release. That's why, you know, in these plots, you can see the beginning of release times are different. This was a May 19th release. This was a May 29th release. This was a June 4th release. So we created this matrix of simulations and then did an analysis.
So what about in the instance of like storms? Do storms ever come through and mess up your data recording?
Yes, sometimes. We actually have, I haven't talked about, you know, on the slide, but there are, for example, high frequency radar stations that are looking out in the water to measure currents, basically. And most of the time before storms, you know, we have to go out and take some of these stations down so that, you know, they won't get damaged or impacted. But there are ocean buoys. National Data Buoy Center is at Stennis, actually. And there are buoys out there on the ocean that are most of the time storm resistant. Of course, some, for example, during Katrina, some of these buoys were impacted. They drifted off or whatnot, and then they had to be picked up. But the important thing is, if they remain in place, especially in storm scenarios, they actually provide really crucial information. And nowadays, gliders, underwater vehicles, autonomous vehicles are used. And before a storm comes, you know, they deploy multiple underwater vehicles into the water along the track of the storm, so that actually they can capture information as the storm is approaching, and then they provide models with. Some of this data gets assimilated right away into the modeling systems. So I haven't talked much at all about data assimilation, but both satellite imagery and data coming from station measurements or autonomous vehicle measurements, models actually correct themselves according to those, because those are reality, right? So, and that's the assimilation step that's happening. That model solution gets improved by merging measurements with model output.
Wow, that's really cool. I don't see any other questions, so I think that we'll wrap it up. Thank you all for joining us, to all of our participants, and thank you again, Kemal, for joining us last week and this week. We really appreciate all of your insight and your information. So we will be back again tomorrow at 1 o'clock for biological oceanography, and then we will have a 3 p.m. speaker as well. So please come back and join us virtually for our week 2 of Blue Planet. So thank you all for joining us, and we will see you tomorrow.